In this video, I'll be going over number 4 in problem set 2. And in this one, we have another reaction with enzymes. And so this figure here is showing the catalytic intermediates in the reaction of a novel serine carboxypeptidase. And so we're trying to grade down what is known as microsin C7. So we're trying to grade that down using our enzymes. And so first of all, A is pretty simple, and it just asks what are the amino acid residues at positions 118, 220, 243, 247, 294, and 311. So, and then to give the full names, the 3-letter abbreviations, and the single-letter abbreviations. So you might have to tap back into exam 1 stuff and just be able to tell amino acids by their R groups, right? So in 118 we notice that we have a serine. In 220 we notice that we have an arginine, asparagine. Okay, asparagine. In 243 we have a glutamate. In 243 we have a glutamate. In 247 we have a lysine. You can tell by that long chain. In 294 we have an arginine. And in 311, this is the one that we should know the most right now from number 3, we have a histidine. So that's that for A. Now for B, it says that the 4 panels, these 4 sections, A, B, C, and D, they're, let me straighten this out real quick. Okay. They are, they're scrambled. They're not in the right order. So you have to put them in the right order first, okay? And then you have to give the role of serine 188 and histidine 311. Okay, so the first step is you just have to figure out the first step, and then it gets kind of easier from there. So the first step would be, what do you guys think it would be? Here in this one, it seems like things are already kind of going on. In this one, it seems like things have already kind of started. So basically, you want to find out what this is resulting from. And that would result from something that looks like this, right? You have a base right here that is abstracting the it's abstracting the hydrogen from this proton, and then this O oxygen gets a negative charge because of the extra electrons now as lone pairs, and then it will attack the carbonyl group, causing this double bond to break and those green lone pairs to go up. And so that's what kind of results in something that looks like this. So we know that this right here is the first step, okay, and then this one is the second one. So then what happens from there? Does this one resemble here? Like this reaction doesn't seem like it happened just from this one, but this one does. This negative charge will come down, and since carbon can't have 4 bonds, it will sever its bond here, which will then just come onto the nitrogen, and that will separate. Okay, and then last but not least, you'll have the water. So you'll have the base then. So you have a double bond here now, and then the base will again abstract the hydrogen from the water, causing a negatively charged OH group, which will then come in here and attack the carbonyl carbon. So then this one would be 3, and this one would be 4. So like in the problem set, instead of writing this all out, you can just put like DBAC. All right, now we have to look at the role of serine 188. So let me find that real quick. Serine 188. I believe that's a typo. I think they meant 118. And we have to find the role of histidine 311. Okay, so we have the histidine here. And we have the serine here. So in a general base catalysis, what happens is you have the base, okay, and what that will do is it will abstract the hydrogen off of this, or off of any entity such as H2O, making OH minus, or even off of this, and that will create a negatively charged entity, a good nucleophile, which will then attach itself onto this carbonyl carbon. And then later it will disattach when these lone pairs come back down. Or what you're interested in cleaving off will disattach when these lone pairs come back down, because it's the best leaving group. So that describes a base catalysis or a base acid catalysis. So they're both kind of participating in that together, serine 118 and histidine 311, because histidine, so serine serving as the acid, histidine serving as the base, which is abstracting the proton from the acid, creating a very good nucleophile to attack the carbonyl carbon. And then once that happens and the lone pairs go up, then when they come back down, then the area that we're interested in will cleave off. So these two together are participating in, they're both in acid-base catalysis. Next question is kind of tricky because we haven't really discussed this part of the reaction much yet, but it says, in which EC class does the enzyme belong? So if you take a look here in this final step, we're using water to cleave, to make the final reaction step. And so what's going to happen is the base is going to abstract this hydrogen, creating a negatively charged OH group, which will then attack the carbonyl. So then the base will have gained an H, and this whole thing will have gained an OH right here. So a hydrolase reaction, or a hydrolytic enzyme, a hydrolase or a hydrolytic enzyme is the enzyme that catalyzes the hydrolysis, or cutting of the water, of a chemical bond. So that's where you have two things together, like A and B, and then you add the H2O, the water, and then what that will do is it'll create A with OH and B with H. So that's essentially what's going to happen here, that this B will end up with the H, and then this A will end up with the OH right there, part of the carbonyl carbon. So I think that'll prompt these lone pairs to go up, but then they'll come back down. So that is C. In D, it says that we're basically we're doing mutations to the enzyme at different places, right? So in the wild type is just this normal enzyme that we have right here. We're not going to affect anything. But then we're doing a mutation to 220, we're doing a mutation to 247, we're doing a mutation to 118, and we're going to see whether or not the efficiency of the enzyme compared to the wild type or the normal enzyme without any mutation, we're going to see if the mutations will slow down the efficiency. Okay, and it gives us this table, so let me draw that out for you. So we're trying to see how, so we're basically putting a mutation at these sites on the enzyme, so 220, 247, 118, and we have the resulting Km and Kcat, and ND here means that ND means no activity. Okay, so the question is, what is the effect of these mutations on the efficiency of the enzyme compared to the wild type? Okay, so if you guys remember the formula for catalytic efficiency, you know that catalytic efficiency is equal to Kcat over Km. So I can quickly explain why how efficiency is equal to this, right? So you want an enzyme to be two things. You want it to be really fast, and you want it to be very specific for your substrate. You want it to have a high affinity for your substrate. So Kcat describes the last step of the reaction that leads to the products. So if I have enzyme plus substrate, and that leads to the ES complex, and then that second step leads to the enzyme plus the product, then K2 here is equal to Kcat. It's always the last step that basically yields the product, okay? So if you maximize Kcat, that means that you're maximizing the number of products that can be made. That all the enzymes together are making the product, and they're all working basically. So it's also known as the turnover number. Km describes the affinity an enzyme has for its substrate. So the higher the Km, the lower the affinity an enzyme has for its substrate. The lower the Km, the higher the affinity an enzyme has for its substrate. So and the thinking behind Km is this. I'm going to draw a very simple Michaelis-Menten chart for an enzyme. Okay. So, velocity here is not how fast an enzyme is working. Velocity here is the number of products made per second or per minute. So, velocity here is the number of products that are being made per second, dependent on the substrate concentration. So if I basically have 10 enzymes in a jar, and I put in one substrate, then one product will be produced. If I put in two substrates, then two products will be produced. So in the beginning, it's proportional, but then it starts to slow down because if I put, let's say, 15 substrates in a jar, only 10 products will be produced because I have 10 enzymes in the jar. So even though I have more substrates than products, the enzyme is limited by the number of, the reaction is limited, the velocity of the reaction, or the number of products made per second, is limited by the number of enzymes in the jar. So let's say I have 10 enzymes in the jar, well, that's the saturation point. Even if I have 1,000 substrates, I can only make 10 products per second because I have 10 enzymes in the jar. So Km is the substrate concentration at which you hit half of Vmax. So this right here, this is Vmax. It's the max velocity. So then half of that is right here. So this is 1 over 2 Vmax. And the point there, will, this will be the substrate concentration. So that's Km. So Km is kind of concentration. It's a concentration symbol. So it's the substrate concentration that takes to get to half of maximal velocity. So that means that if I take a lot of substrate, so let's say my Km is like way down here. If I take a lot of substrate just to get to half of the velocity, half of max velocity, then that tells me that something's not as efficient as it should be. That the affinity between the affinity between the enzyme and the substrate is not very strong. Okay, so a higher Km means it takes a lot more substrate to get to half of your Vmax, and that kind of shows that they really don't want to carry out this reaction. They don't have a high affinity for each other. Whereas if I just add a little bit and I'm already at half of Vmax, that means it's working. Substrate and enzymes, they're really working together to get to Vmax. So a higher Km is a lower affinity, and a lower Km is higher affinity. So in this case, if we want an enzyme that's very fast and very specific for its substrate, or has high affinity for its substrate, then we would want a high Kcat and a low Km. and that's why efficiency overall, a higher efficiency is determined by these two factors in a quotient. Okay, anyway, so I want to find the catalytic efficiency by calculating this for all of these. So then what you would just do is you would just do kcat, you would make a new column, and it would be kcat over km. Now one thing to be careful of is that you want kcat to be in molarity, not in micromolarity. So you want to convert this into molarity first and then divide it by km. So then the units for this is molarity inverse, second inverse. Okay, so that is that's a column that you have to make right here for all these values. Okay, and what you guys will notice is that the value here will be a lot bigger than these two values. This is not even working. This enzyme doesn't even work if you mutate this region. So here you'll get ND, but then here these values will be a lot smaller than this top value. So that'll tell you that all the residues that are mutated here, they're all very important to the functioning of the enzyme. They're all very important. They maintain the catalytic efficiency of the enzyme, and when they're mutated, the efficiency drops. Okay, so they're important in the catalytic mechanism that we just looked at in the last problem. Okay, the last question asks, what is the rationale for mutating the residues present in the wild-type protein to alanine? So basically, what would happen if I were to take, let me see if I can grab it. Oops, okay. If I were to take this reaction, and for every residue, instead of having these side chains, what if I just, instead of all of those, I just had alanine, CH3 as a side chain? What would happen to the efficiency? Well, you will no longer be able to catalyze this reaction, right? Because you need this acid-base property to carry out the reaction, to carry out the catalysis of the substrate. So if you just have CH3 and CH3 here, then those are no longer going to carry out their catalysis, right? And so your catalytic efficiency will be decreased. Okay, so that's the end of this video, and yeah, see you next time.